The problems of engine induction system icing, particularly on engines which are fitted with carburetors, have been known for some years, but accidents still occur in which this factor has been the primary cause. This diagram shows the range of temperatures and the different power settings within which induction system icing can affect the engine. Note that when conditions of high humidity, more than 50% relative humidity, occur in temperatures ranging from as low as minus 17 degrees Celsius, that's 0 degrees Fahrenheit, to as high as plus 37 degrees Celsius, 98 degrees Fahrenheit, engine icing may occur at almost all power selections. This temperature and humidity range occurs throughout the year in areas of the United Kingdom and Europe, and therefore pilots should be constantly aware of the possibilities of induction system icing and take the corrective action necessary before any problems arise and the situation becomes irretrievable. Once an engine stops due to the formation of induction system icing, it's most unlikely that it can be restarted in time to prevent an accident, or, at the very best, a forced landing. The ability to recognize and correct the problem is therefore vital. All pilots operating piston-engined aircraft should understand the issues associated with each particular type of induction system icing, but they also need to know how the engine will react once heat is applied to either prevent or eliminate induction system icing. Basically, there are three forms of engine induction system icing. Impact ice, which results from water which is present in the atmosphere in the form of snow, sleet, or supercooled water droplets. Because of the inertia of the water which causes it, impact ice forms on surfaces which obstruct or change the direction of the induction airflow. Carburetor icing, sometimes called refrigeration icing, which forms mainly in float-type carburetors, where the fuel is injected into the venturi upstream of the throttle valve. It results from the sudden temperature drop caused by both fuel vaporization and pressure reduction in the venturi, combined with the moisture content in the atmosphere. Fuel icing, which is caused by moisture in the fuel coming out of suspension and being frozen by the low temperatures in the venturi of the carburetor. This ice tends to stick to the inlet manifold around its corners and will reduce air and fuel flow into the engine. The indications to the pilot of any form of induction system icing, if he has failed to anticipate the problem, would be a gradual drop in engine RPM, which may be accompanied by engine rough running and vibration. In an aircraft which is fitted with a constant speed propeller, ice formation would be indicated to the pilot by a drop in manifold pressure or a reduction of airspeed in level flight. The problem is caused partly by the rapid cooling in the throat of the carburetor as heat is absorbed from the air during the vaporization of the fuel, and also by the low pressure area in the venturi tube. The result is that the temperature in this area of the carburetor drops as much as 22 degrees Celsius, or 38 degrees Fahrenheit, below the temperature of the incoming air. If now the air contains a large amount of moisture, this cooling process may be sufficient to cause ice to form in the area of the throttle butterfly. This ice formation will reduce the area of the induction intake at this position. It may also prevent the throttle butterfly rotating, which could possibly result in a loss of power, and, if the situation is not corrected, the ice may accumulate sufficiently to block the intake completely and stop the engine. At outside air temperatures of minus 10 degrees Celsius, 14 degrees Fahrenheit, or below, any moisture in the air will be already frozen and will pass through the carburetor, thus carburetor heat should not be used. Carburetor heat does not provide instant relief when it's applied after ice has formed in the system. When induction system icing is suspected, the carburetor heat control should be selected on or hot, and left in this position for sufficient length of time to clear the ice. This could take up to 1 minute, or even longer, depending on the severity of the situation. Partial heat should not be used unless the aircraft is equipped with a carburetor air temperature or CAT gauge. The carburetor heat control provides heated air from the region of the exhaust pipe into the induction system, which will melt the ice. The ice then passes through the engine as water. Engine roughness and further power loss may occur as the water passes into the cylinders, and pilots should not be tempted to return the heat control to off or cold, thinking that the situation has become worse since they applied carburetor heat. Icing is also more likely to occur during long periods of flight at reduced power, such as during a glide descent or a letdown to an approach and landing. This is because the heat required to melt the ice is derived basically from the engine, and during long descents the amount of heat available will diminish, thus reducing the effectiveness of the hot air system. Where icing conditions exist in the atmosphere, select carburetor heat to on before reducing power, so that maximum benefit is gained from the hot engine before its temperature starts to reduce. To help maintain engine temperatures and provide sufficient heat to enable the system to melt any ice, it's necessary to increase power periodically to a cruising setting at intervals of between 500 and 1000 feet during the descent. Additionally, this action prevents fouling of the spark plugs. Induction system icing can occur during taxiing at small throttle settings or when the engine is at idle RPM. In these circumstances, the pilot must ensure that carburetor heat is used before takeoff to clear any ice. The pilot must, however, ensure that carburetor heat is selected to off before opening the throttle to full power and check that the correct takeoff RPM or manifold pressure is obtained. Under no circumstances should carburetor heat be used during takeoff. When using carburetor heat, there are a number of factors which must be understood about its effects. The application of hot air into the induction system caused by the selection of carburetor heat reduces the power output by approximately 15%, and also creates a richer mixture which may cause rough running. Heat should not be applied at power settings greater than 80%, as there is a danger it will cause detonation and, as a consequence, engine damage. Having said that, it should be remembered that induction system icing should not occur anyway at power settings which require a wide throttle butterfly opening. The continuous use of carburetor heat should be avoided because of both the change of mixture strength and also the increase of engine temperatures it causes. Heat should only be used for a sufficient period of time to restore engine power to its original level. This restoration of power when the control is returned to off will be indicated to the pilot by an increase of engine RPM, or by the manifold pressure increasing to above the original setting. Once clear of icing conditions, do not use carburetor heat, but do check periodically that ice has not reformed. An engine fitted with a fuel injection system should not experience the problems associated with fuel or carburetor icing, because the fuel is injected at the cylinder head, where there is sufficient heat for fuel vaporization, and to prevent freezing of any moisture released. Other parts of the induction system, however, may accumulate ice, which will give similar loss of power indications to those suffered by a carburetor system. For instance, impact ice may gather on the air filter, or bends in the system, particularly when the aircraft is flying in cloud at low temperatures. Ice may also accumulate round the throttle valve when operating at low throttle settings in high humidity conditions. The alternate air system, which is almost inevitably fitted to these engines, should then be selected, and the icing drill followed according to the aircraft checklist. Use of the carburetor heat control on the ground should be kept to a minimum, because the air then fed into the engine is not filtered, and thus may feed dust and dirt into the system. This will cause heavy additional wear on the pistons and cylinder walls. A functional check of the carburetor heat control should be made before takeoff. The indications obtained during the check, providing there is no ice present, are that the engine RPM will drop by approximately 100 RPM when carburetor heat is selected to on or hot. The engine RPM will only return to the selected setting when the carburetor heat is selected to the off or cold position. If icing is evident on the ground before takeoff, use carburetor heat to clear the ice, but return the carburetor heat control to off or cold before applying takeoff power. A positive check that normal takeoff power is available must be made after using the carburetor heat system in this manner. Do not use carburetor heat during the climb or at power settings above 80%. Be aware of conditions which are likely to cause induction system icing: damp, cloudy, foggy or hazy days, or times when you're flying either close to cloud or in rain or drizzle. Be alert for an unaccountable loss of engine RPM or manifold pressure. Make frequent checks for induction system icing by selecting carburetor heat on for a period of between 15 to 30 seconds, noting the engine RPM prior to system selection, then the subsequent drop of engine RPM as heat is applied. Listen to the engine noise and check if the outside air temperature is within the range where you might expect induction system icing to occur. Should either the engine RPM increase when heat is applied, or the engine RPM return to a higher figure than was apparent when carburetor heat was last selected off, then ice is present in the induction system. Continue to use carburetor heat while flight in icing conditions continues. Apply carburetor heat during glide descents or long periods of flight at reduced power, that is below 1800 RPM, remembering to warm the engine by opening the throttle for short periods every 500 to 1000 feet. The carburetor heat selector should remain at off during the approach and landing, except for when making a glide approach. But if icing conditions are known or suspected, carburetor heat should be selected on. However, the carburetor heat control must be returned to off or cold before applying power during a roller landing or when carrying out an overshoot. During hot or dry weather conditions, selection of carburetor heat may cause the engine to suffer a rich cut because of the sudden imbalance which it will cause to the mixture strength. You must therefore use the carburetor heat control sensibly, not just as a matter of habit. Think about what you're doing and check the prevailing conditions. This concludes the lesson on engine icing.